Hello students, hope you all are fine and you must be going through our videos, the full course videos that we have uploaded in our website. Plus you must be following the practice tests that we have in store for you. Now needless to remind you that whatever clarifications you need on the various topics, you can always refer to them through our interactive online as well as offline sessions. And for you guys out there, Aptdemy is accessible. The e-platform is always accessible to you 24 by 7. And we have introduced a number of courses, AP courses. We have the SAT, GLE, GMAT, BIT, VIEEE, the SET courses, and many such other courses in store for you. So please refer to Aptdemy to your aspiring friends as well as other students who are interested in the various courses. So the best part, students, today is that we are going live. We shall be solving some problems on current electricity. And to remind you all that we are offering a 25% discount on our registration fees, on the course fees, in fact, if you are registering on or before 31st of July. And for meritorious students, we also offer 100% scholarship programs. So kindly follow after me and let's begin the course today with two interesting problems on current electricity. Now before I begin, I'd like to recall what is current electricity basically, and in this chapter, what type of problems do we target. Now as we know, charges, they can be in rest as well as in motion. So whenever we are talking about charges, electric charges, in fact, the concept of current comes into mind. Current is nothing but the rate of flow of charge per unit time. So whenever we are talking about current that powers our homes as well as electrical devices, then a number of problems associated with that comes into point. Now let's begin with one such problem. In the balanced condition, the values of the resistances of the four arms of a Wheatstone bridge are shown in the figure. The resistance R3 has temperature coefficient 0.0004 per degree Celsius. If the temperature of R3 is increased by 100 degrees Celsius, the voltage developed between S and T will be how much? So let's look at this beautiful problem that we have. Now, here, if you can see the diagram that we have a cell of potential 50 volts and it has been connected to resistances in two different arms. You can see R1, R2 of value 60 ohms and 100 ohms, and we have R3, R4 arranged in such a way that the balance, the Wheatstone balance, in fact, the bridge is balanced condition, is in the balanced condition. You can even note that we have R1 by R2 as 60 by 100, which gives us a value of 3 by 5. And similarly, you can see that R3 by R4, if it is worked out, we get it as 300 by 500, which is again 3 by 5. So we can see from the diagram itself that the Wheatstone bridge is balanced in this case. Now keeping in mind at the balanced position of the bridge, we need to find out the potential difference between the points or the terminals S and T. So looking at the resistance R3, you can see that the resistance R3, it has a temperature coefficient which is indicated by the letter alpha, and alpha is equal to 0.0004 per degree Celsius. The temperature changes by 100 degrees Celsius, or we can say that delta T, which is indicating the change in temperature as 100 degrees Celsius. Now this tells us that the resistance R3, depending on temperature, it will get modified. Say it becomes R3 dash, and R3 dash is nothing but equal to R3 times 1 plus alpha times delta T. So let's work this out. We have R3 here as 300 times 1 plus This is alpha as 0.0004 multiplied by 100. So working this out, we get R3 as equal to 312 ohms. So we see that R3 has got modified to R3 dash. Now, looking at the currents which are passing through the respective circuits, let's have a look at the current. If you see, this is the positive terminal of the cell, which means that the current is coming out in this way. At this point, there is a break in the circuit, which suggests that a part of this total current I is passing through this part of the circuit. Let us assume that part as I1, and the other part of I is passing through this, the right hand side of the circuit. So we can see this part, let us take it as I2. Now, in an attempt to calculate the values of I1 and I2, we apply Ohm's law, that is V equals IR. So let's look at that. We have I1 as equal to V, that's 50 by R. Now, what do we take R as? Looking at the values, you can see that we have R3 replaced by R3 dash. This is in fact R3 dash, which is now equal to 312 ohms, and these two resistances are in series. So we have a net resistance of 312 plus 60, which amounts to 372 ohms. So we see that this is the current which is flowing in the left-hand side of the circuit, the left-hand portion of the cell. So this is how we find out I1. Similarly, in an attempt to find out I2, we see that I2 will be equal to, again, the voltage is 50 by the net resistance here is R2 plus R4, which is 600. Now, we need to find out the voltage that develops between S and T. So, the voltage that develops at S is say given as Vs, and the voltage at the point T is say given by Vt. Then we have Vs minus Vt. This is equal to the, look at the voltage, the potential drop across this part of the circuit. So if you're considering this particular portion, then the potential drop across this portion is given by I1, that's the current in this part, and the potential or the resistance that we have here to find out the potential is nothing but 312. So this is the resistance here, and minus, for this part the potential drop is nothing but 500 times the current in this part of the circuit is I2. So we just now need to put in the values of I1 and I2. We have 312 times I1, which is 50 by 372, minus we have 500 times I2, that's 50 by 600. And when we work this out, we get Vs minus Vt as equal to, let's look at the individual values. This is around 41.94, and for the second part, it's 41.67. So this finally gives us the value of Vs minus Vt, that is the potential difference between the points S and T, comes out to be 0.27 or 0.27 volts. Now moving on to the next problem that we have in hand today, we have a frustum shaped conductor. So let's look at the question. Two resistances R1 equals X ohms and R2 equals 1 ohm are connected to a wire AB of uniform resistivity as shown in the figure. The radius of the wire varies linearly along its axis from 0.2 millimeters at A to 1 millimeters at B. A galvanometer G connected to the center of the wire 50 centimeters from each end along its axis shows zero deflection when A and B are connected to a battery. the value of x is. So we need to find out the value of x here. Now consider the shape of the conductor. You have seen in the question that we have two resistances which are connected to a wire AB, but the wire has got uniform resistivity, but its radius is varying linearly along its axis. So imagine the variation of radius along the axis. Can you imagine? If this is the wire, its shape is varying along the axis. So you can see that this is in fact the shape of the conductor here. And how is the shape varying? Its shape is varying from 0.2 millimeters at A to 1 millimeter at B. So if you consider this point as A and this point as B, the radius here, this is A, this is varying, this is equal to in fact 0.2 millimeters, and here it's B and it is equal to 1 millimeter. Just look at the variation. Also, it has been told that at the center of the wire, we have a galvanometer connected, such that the point at the center that we are considering, that point is at a distance of 50 centimeters from each end. So this distance is also 50 and the remaining distance is also 50. But look at the units. This is in centimeters now. Okay, now what we have here is, let us assume that this is R. Then very easily we can find out R here. R is nothing but A plus B by 2. So we have A as 0.2, B as 1 by 2. So this is nothing but 0.6 millimeter. So you must be wondering why we have found this R out. So you quickly get an answer to this. Now, for a frustum-shaped conductor, now this is a frustum shape. For a frustum-shaped conductor, the resistance that we need to find out. Resistance, we know the general formula as to how resistance is related to resistivity. So we know R equals rho L by A. Here you must be knowing that rho is nothing but resistivity of the material of the wire, which is the same 12. Take a look at this part of the question. It is uniform resistivity. L is the length in fact of the wire, and A the area of cross section. Now here, when we are talking of the frustum shape of the conductor, we need to remember that the value of A is actually given as pi AB. So now, how do we write down the resistance here? Since we have two different portions for this conductor, we will try to write down expressions for the resistances for both the halves. For the first half, that is considering this half, let me take this as the left half. The resistance of left half of the conductor. The formula is the same here. The resistance for the left half, let us take this resistance as P, and this is equal to rho. What will I choose the length as? We are considering the left half, so the length is nothing but 50 centimeter. Let us change that to meter. We have 50 times 10 to the power minus 2. Centimeter changed to meter. Then we have pi in the denominator. A times B. Now what is A here? This is 0.2 millimeters. We will change that to meter, multiplying it by 10 to the power minus 3. And B. Now see, B is not this B that we are talking about. We are considering these 2 points. So B here is actually R. And R we have found it out as 0.6 millimeter. So this is 0.6 times 10 to the power minus 3 again. As we are targeting that we will be doing the sum in SI units. So this is the value of the resistance of the left half. Now looking at the resistance of the right half of the conductor. is nothing but equal to Q. Say. And we have that as rho. What's L? L is again the same, 50 centimeter. So 50 times 10 to the power minus 2 meters by, again, pi AB. What's A now? A is nothing but this point, which is R. That's 0.6 times 10 to the power minus 3 times B, which is 1 millimeter. That is 1 times 10 to the power minus 3 meters. So we have successfully got the, or written down the expressions for the resistances of the left half and the right half of the conductor. Now time to apply the balanced Wheatstone bridge principle. So let's begin with that. Now, for the bridge to be balanced, the condition is that the resistances in the two arms are R1 and R2. So we have R1 by P equals R2 by Q. This is what we have, and R1 has been given as X, by P is this, that we put in the value, rho times 50 times 10 to the power minus 2, and the whole thing going up, we have this as pi, then 0.2 times 10 to the power minus 3 times 0.6 times 10 to the power minus 3. And looking at the second part, this is equal to R2, which is nothing but 1 times or by Q. So Q is this, we have rho times 50 times 10 to the power minus 2, and in the numerator we have pi times 0.6 times 10 to the power minus 3 times 10 to the power minus 3. So look at the common terms getting cancelled out. Wonderful. So we have 0.2x is equal to 1, or x is equal to 1 by 0.2, that's equal to 10 by 2 or 5. So we can very well see that the value of x comes out to be 5. So two wonderful problems. But before ending, let me remind you, our online registrations are going on. So stay tuned with Aptdemy and keep supporting. Thank you.